Multiple supervolcanoes are waking up at the same time, and scientists didn't see it coming. At noon, the sky went gray. Flights stacked in holding patterns, then vanished from radar as ash shut the air. Street lights flicked on at lunchtime. People coughed, phones buzzed emergency alerts, and a fine grit settled on everything. This isn't Yellowstone. It's somewhere no one expected. Here's the promise. The clock that says we're overdue, the hidden magma highways that feed giants, and why scientists can't stop what's already moving. To understand a blast like this, we go deep, down to mantle plumes and stalled magma. The stakes are simple: food, climate, and a supply chain that snaps fast. Let's go. What counts as a supervolcano? We don't call a volcano super because it's tall. We call it super because of what it does to the world. The working line is the Volcanic Explosivity Index, VI, where an 8 means at least 1,000 cubic kilometers of ejecta. That's enough ash and sulfur to dim daylight, cool oceans, and choke harvests across continents. It's not a mountain, it's a system, often flat, often drowned, sometimes hidden in plain sight under lakes or grasslands. You can stand on a supervolcano and not realize it. Caldera rims blur into gentle hills. The danger isn't a peak. It's a vast, shallow reservoir of crystal-rich magma, more mush than melt, waiting for pressure to rise and bubbles to link arms. When that happens, the roof fails. The eruption column roars upward until it collapses. Ignimbrites race outward, and the sky trades blue for ash. The human scale? Air that scrapes your throat, feels blanketed, water-clogged, and a sun that feels weak even at noon. We've seen footprints. Around 74,000 years ago, Toba left a smear of ash from the Indian Ocean to East Africa and loaded the stratosphere with sulfur. Taupo in New Zealand blew at VI8 with the Orwanui eruption, and later at VI7 with Hatpé. Yellowstone has records, Huckleberry Ridge, Mesa Falls, Lava Creek, that turned parts of North America into pumice plains. Not all of these look like volcanoes. Many are basins, lakes, or quiet meadows with hot streams threading through them. People want frequency, a schedule that fits a calendar. The truth is messy. Super eruptions are rare, but they cluster in geologic time. Their intervals stretch beyond civilizations, so our records are patchy. We get hints from ash layers, ice cores, and scattered pumice rafts. And even then, the picture looks more like a heartbeat, with long pauses and sudden flurries than a metronome. Why does the label matter? Because impact decides response. A VI8 is the top tier, but a VI7, an order of magnitude smaller, can still punch the world. Sulfur dioxide builds a bright veil that bounces sunlight away. Temperatures dip, growing seasons compress. Ships stall as ports close under ash falls, and planes don't fly through glass-rich dust that melts in jet engines. Food isn't just crops, it's the chain. Fertilizer, diesel, cold storage, logistics that keeps calories moving. One weak link under ash and we feel it globally. There are misconceptions. Supervolcano doesn't mean it erupts like clockwork, and it doesn't mean a single explosion wipes everything clean. These systems breathe. They lift and sink by centimeters and meters over years, vent gas without headlines, and blow smaller caps, VI4s, 5s, 6s, that reset the plumbing. Each event moves pressure around. Each intrusion of fresh magma adds heat, volatiles, and new stress. Under the headline, label, sits the engine. The reservoir isn't a single pool. It's a sponge of crystals, soaked with melt, stacked in layers, recharged by deeper inputs. If gas saturates, if pathways open, if the roof weakens, the system can tip. But it's not just vertical. Melt takes detours. It collects in sills, sneaks along weaknesses, and sometimes it simply stalls, charging the battery without turning on the light. That stalling is why we can have centuries of calm while pressure still rises. So what counts as super? Impact that reaches across latitudes. Eruption volumes that redraw weather for years. Ash blankets that cross oceans. A footprint visible in ice in Greenland and Antarctica. The names we use, Toba, Taupo, Yellowstone, are handles for sprawling, evolving systems. The real definition is what they do to people. Air too dirty to breathe without filters, fields that won't grow for seasons, and a sky that forgets its color. And yes, the frequency. Rare doesn't mean never. When we map the last few million years, the count of VI8s is small. but the count of VI 6s and 7s is large enough to matter for modern life. We built our civilization during a relatively quiet chapter. We lengthened supply lines, tightened inventories, and optimized for efficiency over buffer. That's fine when the sky behaves. It's fragile when it doesn't. Labels are the start, not the answer. Because the real story isn't the crater, it's the pipeline. If we want to understand who reloads, who stalls, and who's primed, we have to go below the crust. We have to talk about heat rising from deep time and the arguments about how it gets there. The names change. Plumes, plate edges, slab windows, but they all point to the same question. What's feeding these giants? The Mantle idea and its rivals. To understand who feeds these giants, we start with a simple picture. Hot rock rising because it's lighter. That's the Mantle plume idea. Deep in Earth's mantle, maybe near the core mantle boundary, heat builds. A narrow, buoyant column starts creeping upward like a slow-motion lava lamp. As it rises, it expands, it softens surrounding rock, and near the surface, it releases melt. Over millions of years, that can carve hotspot tracks, flood basalts, and crucially, refill crustal mush zones that become our calderas. In the plume world, there are two main parts. First, a big bulbous head that arrives with a surge of heat and melts. Think continent-scale basalt outpourings in deep time. Then a thinner tail that keeps a region supplied for tens of millions of years, leaving a trail of volcanoes on a moving plate. The Hawaiian Emperor chain is textbook. The plate drifts, the plume stays, volcanoes wink on and off as they pass over the hotspot. If you can draw a line of progressively older lavas heading away from a current volcano, that's plume logic at work. But Earth isn't a textbook, and rival models push back. One says we don't need deep fixed heat pipes. Plates themselves create their own hotspots. At edges where thick continental lithosphere thins next to oceanic plates, you get edge-driven convection, shallow rolls of mantle that locally concentrate heat and melt. Another rival is the slab window. When a subducting plate tears or a mid-ocean ridge dives into a trench, gaps open beneath the overriding plate. Hotter asthenosphere flows through those windows and makes melt without a deep plume. There's also delamination, when the dense root of a mountain belt peels off and sinks. That drop pulls hot mantle up to replace it, again making melt. These aren't academic quibbles. Prediction depends on which engine is real in a given region. If you're dealing with a long-lived plume tail, you expect steady, deep heat and helium-3 signatures that whisper about the mantle's primordial reservoir. If edge convection or slab windows dominate, the supply might pulse with plate motions, accelerating or stalling as boundaries reorganize. Get the engine wrong, and you misread the reload rate of a caldera. So, what's the evidence? One clue is helium. Helium-3 is scarce on Earth, most of it is primordial. High 3 He-4 He ratios in volcanic gases hint that the melt tapped deeper, less degassed mantle, often cited for plumes like Hawaii and Iceland. It's not a smoking gun, but it's suggestive. Another clue is seismic tomography. We listen to earthquakes and map how fast seismic waves travel. Slower waves mean hotter, maybe partially molten rock. In some regions, we see slender, low-velocity columns reaching down hundreds of kilometers plume candidates. Elsewhere, we see broad, messy patches that look more like plate-driven upwellings than tidy conduits. Then there are hotspot tracks. The Hawaiian chain ages neatly with distance, but other hotspots smear and wander. Yellowstone's track, the Snake River Plain, lines up with North America's motion, yet the imaging under Yellowstone shows a complex, tilted, low-velocity body that doesn't neatly punch from the core mantle boundary. That drives debate. Deep plume tilted by mantle flow, or a plume interacting with slabs, or instead a shallow return flow enhanced by the tearing Pacific slab? The answer matters for how much heat is still coming, and for how it's distributed. Here's a human-scale micro-story from the science trenches. A graduate student stares at a blue and red tomography slice on a midnight screen. The plume's shadow is barely there, fuzzy, stitched from thousands of tiny quakes. She reruns the inversion with a different damping parameter. The column sharpens, but now the base disappears into noise. She sighs, circles a region, and writes in her notebook. Feature or artifact? The next morning, a helium dataset arrives from a field team. Ratios are high, but they're mixed with crustal helium. She writes another line, signal, but messy. That's plume science. Never a single map, always a cross-exam of imperfect witnesses. Rival models carry their own fingerprints. Edge-driven convection should cluster melts along lithospheric steps. Slab windows line up with plate geometries you can trace with earthquake foci and subducted slab outlines. Delamination leaves geochemical marks, elevated iron, certain isotopes, that point to mantle upwelling minus the deep, primordial helium spike. When multiple lines of evidence converge, helium ratios, tomography, plate reconstructions, geochemistry, you can argue for one engine with more confidence. There's also a hybrid reality. Plumes don't rise into a vacuum. They hit moving plates and subducting slabs. In the North Atlantic, Iceland straddles a ridge and a plume. Interaction between the two boosts melt production, spreads it along the ridge, and creates magma-rich corridors northward. In the central Mediterranean, the subduction geometry is torn and contorted. If deeper anomalies exist, they're bent by slabs and mantle flow, squeezing melt toward weak crustal zones like Campi Flegrei. These aren't neat cylinders. They're smeared highways with on-ramps and detours. Why does this fight over engines belong in a story about supervolcanoes? Because fuel lines decide which calderas recharge faster, how wide the catchment of melt really is, and whether pressure builds steadily or in bursts. If a caldera plugs into a deep, steady supply, then even quiet decades could mask a long, slow inflation of the battery. If it's fed by plate reorganizations, then watch for the tectonic shifts, slab rollback phases, ridge jumps that change the melt faucet. There's one more twist. Melt moves in stages. Deep upwelling makes partial melt. That melt percolates upward, ponds at density traps, crystallizes, releases volatiles, and moves again. Each stall is a chance for pressure to accumulate, a place where a distant pulse of heat can show up months or years later as gas flux or subtle uplift. If the highway exists, we should be able to map its exits, the sills, the lenses, the mush zones that light up before a system tips. That's our next step, tracing the hidden global magma network that ties distant engines to local crises. The hidden global magma network. If plumes and plate edges are the engines, the road system is stranger, a lattice of warm, weak rock where melt can gather, linger, and move sideways for surprising distances. Seismic tomography doesn't show glowing rivers of magma. It shows low-velocity zones, volumes where seismic waves slow because the rock is hotter, softer, and in places sprinkled with melt. Stitch enough of those zones together and you start to see corridors. Not pipes, corridors. Mushy, leaky pathways that link deep sources to shallow traps. Think of the crust and upper mantle, not as solid blocks but as a layered sponge. Melt collects where density and stress let it. In the lower crust, it spreads into sills, flat intrusions that can span tens of kilometers. Above that, melt pools and lenses, coalescing into crystal-rich mush zones. These aren't empty chambers. They're saturated frameworks with melt weaving through crystal scaffolds. A nudge in pressure opens pore spaces. A cooling step crystallizes more, squeezing fluid elsewhere. The network breathes. Tomography hints at this breathing. Under Iceland, a plume-rich mashup feeds a broad swath of low-velocity mantle that trends north toward Jan Mayen and south along the Reykjanes Ridge. Under the central Mediterranean, slow zones drape beneath the Tyrrhenian and Campanian crust, guided by broken slabs. Under the western United States, a tilted low-velocity sheet angles from the mantle toward Yellowstone's crustal reservoirs. But it spreads, thins, and thickens as it hits old tectonic scars. None of these look like straight tubes. They look like weather maps for rock, fronts, eddies, and gradients. What nobody knew until dense arrays went in was how interconnected some of these slow zones appear. Deploy thousands of seismometers across continents. Run adjoint inversions on petabytes of waveforms, and patterns emerge. Patches that brighten and dim together in different datasets. They aren't turning on and off like lights. They're changing enough to suggest temperature shifts, melt redistribution, or both. When gas flux rises in one caldera and subtle uplift starts in another 1,000 kilometers away, the reflex is coincidence. But layer the signals and the timing looks less random. Here's the mechanism. Magma budgets don't move as a single slug of liquid. partial melt percolates upward along grain boundaries, then pools at density traps. If a deep anomaly warms a broad area for a few thousand years, crustal sills accumulate more melt and volatile-rich pockets get larger. Eventually, they connect. A pressure pulse, maybe from fresh basalt underplating, maybe from volatile exsolution as crystallization advances, can move laterally through the network like a slow wave. Not at highway speeds, at human lifetime speeds. Months to years for shallow sills, decades for deeper mush. That's fast enough to matter for monitoring. Field evidence backs the network idea. In rift zones, you'll see dike intrusions migrate laterally for tens of kilometers, stepping through linked weaknesses. In arc systems, geochemical fingerprints show mixing between melts from different depths and sources. Slab fluids, mantle wedges, and crustal remelts, blending in shared reservoirs. INSAR maps reveal broad, saucer-shaped uplift that's hard to explain with a single round chamber. It fits better with stacked sills, inflating across wide areas. Even micro-earthquake swarms sometimes zip along lines that mirror mapped sills, like someone tracing a hidden seam. Why does this matter for supervolcanoes? Because synchronization risk lives in networks. If multiple calderas sit on shared supply lines, broad zones of elevated temperature and melt fraction, then regional changes can push several systems closer to their tipping points at once. Not to identical outcomes, but to thresholds. One may burp a VI4, another a VI6, while a third just exhales gas and lifts a few centimeters. But stack those outcomes within a decade, and the global impact compounds, aviation reroutes, sulfur-driven cooling, disrupted harvests, without a single VI8. There's also the priming effect. A distant plume doesn't need to send a magma bullet to a caldera to matter. It just has to maintain a background of warmth that keeps melt from freezing. That reduces the extra energy needed for a local recharge event, say basaltic injections from below, to tip a reservoir from mush toward eruptible melt. In that sense, the highway is thermal and mechanical as much as magmatic, a field of softened rock that makes pressure waves travel farther and sills link more easily. Scientists test this with coupled models. They take tomography-derived structures, assign plausible temperatures and melt fractions, and simulate how pressure pulses propagate. The outputs aren't drumbeats. They're slow, damped ripples that amplify near structural traps, fault-bounded basins, old rift fabrics, thick-to-thin lithosphere steps. That's where you'd also expect to see helium wiggles, gas chemistry shifts, and millimeter-scale tilts pick up. If three instruments in different countries nudge in phase, it's a clue. Not proof, but a pattern to watch. Microstory: a remote station on a salt flat records a steady helium-3 rise, then a plateau. 2 weeks later, a caldera across the ocean shows a slight, persistent uplift on INSAR. A week after that, a subduction arc vents more SO2 than its seasonal baseline. Each team shrugs at its own anomaly. A data analyst, sleepless in front of an open dashboard, clicks layers on and off. The timing lines up. She tags the series region-wide priming and emails 5 PIs. The subject line reads, "Maybe not coincidence." The network framing isn't an excuse to predict doom everywhere. It's a way to prioritize attention. Where slow zones connect, where sills stack, where helium stays high, those are nodes with higher odds of meaningful change. It also reframes the old question, where's the next super eruption, into a more useful one, which clusters are edging toward collective stress. One node in this network has history written in ash, and its deposits still fall like a ruler across oceans. We're going there next. Toba's Bottleneck, the worst case we remember. 74,000 years ago, a lake in northern Sumatra became a boundary line in human memory. The Toba caldera didn't rise like a mountain, it failed like a roof. Pressure inside a crystal-rich reservoir reached a point where bubbles linked, fragments multiplied, and the ceiling collapsed. The opening blast drove a column into the stratosphere, a gray fountain tens of kilometers high. Then the column lost strength, folded, and fell back. Pyroclastic density currents raced outward, smothering valleys and rivers at highway speeds. Hours to days later, the landscape was a quilt of ash and welded tuff, and the caldera floor had dropped to make the basin that holds Lake Toba today. We measure that event by what it left behind. Ash thicker than a person across the Indian Ocean basin. A glassy layer traced in ocean cores from the Arabian Sea to the South China Sea. In Africa, a subtle but distinct line of shards layered into sediments along rift lakes. The total ejecta sits in the VI8 range, on the order of 1,000 cubic kilometers, when you count both the ignimbrites and the co-ignimbrite ash that rode the wind. The sulfur was the quiet assassin. It lofted into the stratosphere and spread as sulfate aerosols, brightening the planet and dimming the ground below for years. The climate response wasn't a neat switch, it was a sequence. Sunlight dropped, sea surfaces cooled, monsoon systems weakened and shifted. In some regions, drought deepened. In others, storm tracks slid. Ocean mixing changed as cooler surface waters capped the upper layers. Plants, already living close to the edge in Pleistocene climates, struggled with shorter growing seasons and colder snaps. Herbivores moved, thinned or vanished locally. Predators tightened their ranges. Humans adapted where they could, moved when they had to, and endured a colder, dustier sky. Here's where the human stakes sparked debate. The bottleneck. Genetic studies once seemed to show a sharp reduction in human effective population size, sometime in this window. A bottleneck that some linked to Toba's aftermath. It's a compelling story. A super eruption nearly.
Prunes the human tree. But newer work complicates that picture. Genetic signals can reflect older structure and migration patterns. Archaeological sites in Africa and India show continuity across the ash layer in some places, with people using the same tool traditions before and after. In other places, there's disruption. The honest state of play: Toba was huge. It cooled the planet for years, and it likely stressed human groups unevenly. A single, global, near-extinction event is not supported by all lines of evidence. What's not contested is the sulfur loading. Modeling suggests a multi-year volcanic winter, with global mean cooling of a few degrees in the first couple of years, tapering as aerosols settled and chemistry changed. That's enough to shorten growing seasons by weeks. It's enough to shift rain away from fields that needed it most. In a hunter-gatherer world, mobility and diversity of food sources buffered some of that shock. In today's world, the hit would land differently. Now jump to the modern lens. We've built a food system that's productive and fast, but thin on slack. A Toba-scale sulfur veil would immediately cut solar radiation reaching crops. Wheat, maize, and rice yields drop with lower sunlight and cooler temperatures, especially if it hits during critical growth windows. Ash wouldn't need to bury continents to cause pain. Millimeter-thick deposits on leaves reduce photosynthesis. Ash and irrigation canals clogs pumps. Dairy herds breathe a brace of dust. Fish farms choke as intakes foul. Ports slow, then stop. Insurance markets wobble. A world tuned for just-in-time discovers what just-in-case felt like. Aviation is the nervous system of that chain. Volcanic ash melts in jet engines and coats turbine blades in glass, so pilots will fly nowhere near it. After Age of Yellowstone in 2010, tiny compared to Toba, European flights shut for days. Multiply the ash source, expand it across hemispheres, and flight corridors bend or vanish. Perishable cargo backs up. Spare parts don't arrive. Even power plants feel it when gas turbines can't be serviced and coal deliveries stall. What about the eruption mechanics that made Toba so big? It wasn't just one chamber detonating. The reservoir was a stacked, crystal-rich mush fed by basaltic injections from below. As crystals grew, water and CO2 exsolved, gas came out of solution, raising pressure. Roof faults weakened the lid. When failure began, decompression fed more gas release, a runaway feedback. The caldera collapse didn't merely follow the eruption, it drove it, opening space that allowed more material to erupt. Post-eruption, the system didn't die, it resettled. Hydrothermal systems found new paths. The lake formed. The region still steams. A micro-story closes the loop. In a cave, a continent away, a layer of very fine ash threads a stalagmite. Growth bands above it are narrower for years. The person who cuts and polishes that rock, 74,000 years later, squints at the laminae and marks a ruler along the edge. Each millimeter, a year. The thinner bands after the ash say colder, darker seasons. It's not a myth, it's a calendar. So what does Toba teach beyond awe? First, scale matters. Sulfur rules the global outcome. Second, the pathways to super eruption run through decades of recharge and roof weakening, not surprise explosions from nowhere. Third, the impacts land on systems. People live inside those systems. Today, the same physical forcing would play out through ports, grids, and inventories. And here's the twist. Indonesia isn't the only place with the right ingredients. The next threat might not come from Sumatra at all. Yellowstone. Famous, misunderstood, still dangerous.
Yellowstone sits in the headlines like a loaded question, but the real story isn't doomscroll material. It's a long, complicated breathing cycle with a dangerous middle ground. Start with its past giants. Around 2.1 million years ago, the Huckleberry Ridge event ripped across what's now the Yellowstone Plateau with a VI-8 release that spread ash over much of North America. About 1.3 million years ago came Mesa Falls, smaller but still severe. Then roughly 631,000 years ago, the Lava Creek eruption reshaped the caldera again. Those names sound like a trilogy. They're more like chapters in a slow, shifting engine that kept moving as the North American plate rolled over a deep heat source. Today, visitors see geysers, not pumice plains, and that creates a myth. Either it's overdue for a world ender, or it's harmless because it's just Old Faithful. Neither is right. The ground lifts and sinks by centimeters to tens of centimeters over years. Hydrothermal explosions have hurled boulders hundreds of meters. Seismic swarms rattle the subsurface every year, sometimes by the thousands of small quakes. These are not countdown ticks, they're the plumbing adjusting. Pressure moving through fractures, water flashing to steam, new heat reaching old pathways. The overdue idea refuses to die because recurrence intervals make easy graphs. People take 3 big eruptions, average the gaps, and draw a scary line. But volcanoes don't keep calendars. Recurrence isn't a schedule, it's a range, skewed by how the system evolves. More importantly, Yellowstone's current state is a stacked crystal mush with pockets of melt. Think 5 to 15% melt in places, not a giant vat of liquid waiting like a shaken soda. That percentage matters. To mobilize, you need a connected melt network and enough gas pressure to break the roof. Right now, the balance points to a system capable of smaller, still serious events. So what are the realistic threats? Sub-super eruptions, VI-6, even large VI-7 is a debated upper bound. Wouldn't be cinematic from space, but they'd be brutal on the ground. Picture an explosive event that lofts ash across the central and western United States. Millimeters to centimeters settle over farmland. Power substations inhale abrasive dust. Interstate trucking slows under visibility warnings. Regional aviation hangs on the edge of shutdown as ash advisories redraw routes. Ranchers scrape water troughs full of gray grit. Cities dozens of miles away wash ash from intakes and gutters for weeks. That's not the end of civilization. It's a multi-state crisis with national ripples. There's also the quieter, more common hazard, hydrothermal blasts. These come without magma rising. Hot water trapped beneath a seal flashes to steam and blows out a crater, throwing rocks and mud across a valley in seconds. Yellowstone's landscape is pocked with these scars. They're local, but they hit without long warning, and they define how park managers think about risk where tourists stand close to boiling ground. Underground, the system's shape matters. Seismic imaging shows a tilted, low-velocity body that links deeper mantle anomalies to shallower crustal reservoirs. Not a straight straw, more like a smeared, branching conduit feeding stacked sills and mush zones. Fresh basalt from below adds heat and volatiles, resetting pressure in pockets. That's the reload mechanism. Not a constant pump, but pulses, years to decades apart, where gas flux rises, ground lifts, and swarms shuffle through the caldera's edges. Each pulse is a negotiation with the roof. Does it vent quietly through geyser basins, or does a sealed zone fail more violently? Here's where the network lens returns. While eyes stare at Wyoming, the broader corridor through the western U.S. shows correlated hints. Low-velocity anomalies stretching along ancient tectonic fabrics, gas chemistry shifts at distant springs, upticks in deep seismicity beneath the Snake River plain. None of this screams tomorrow, but together it says, the thermal field that sustains Yellowstone isn't dying. It's being shaped by mantle flow, interacting with old scars in the plate. The system breathes with the region. A micro-story from monitoring brings it close. It's 2:11 a.m. in a small lab stacked with blinking routers. A duty scientist watches real-time GPS traces. A station on the caldera's north rim has crept upward 3 millimeters in a week. Nothing dramatic until she overlays gas data and sees a slight rise in CO2 at a vent line that's usually steady. She flags it, sends a quiet note to the team, and goes back to the feeds. By noon, an earthquake swarm, tiny quakes like tapping on glass, zigzags along a known fault. Park visitors won't notice more than a closed boardwalk. The team's takeaway, pressure moved. The plumbing found a release. Could Yellowstone produce another VEI-8 in our time? The candid answer is that no current line of evidence points to an
eruptible, connected, chamber-scale melt volume ready to do that. The longer answer is that the same engine that made past giants still supplies heat, and geologic systems change on their own clocks. That's why the focus stays on signals that matter: melt fraction, volatile saturation, and pore pressure in key seals. Those are what shift a system from restless to eruptive. So we hold two truths. Yellowstone is famous and misunderstood. It's not a doomsday timer, but it's not a postcard either. It's a restless caldera with realistic hazards that would stress a nation even without crossing the super threshold. And while cameras point at Wyoming, another caldera across the Pacific keeps reloading in quieter ways, with a recent record that's sharper, younger, and closer to the thresholds we watch. Taupo and the Ring of Fire's quiet monsters. While Yellowstone holds the spotlight, Taupo works in the shadows, and its record is recent enough to sting. The Orowanui eruption, about 25,500 years ago, sits at VI-8. It emptied a vast reservoir beneath New Zealand's central North Island, blanketed the landscape in ignimbrite sheets, and sent ash across the South Pacific. The lake you see today is the scar. Even after that, Taupo wasn't done. Around 232 CE, the Heidepe eruption hit VI-7, one of the most powerful in the last 2 millennia. The fallout spread across Aotearoa. Pumice rafts drifted to distant shores. Taupo doesn't rise as a classic cone. It's part of the Taupō volcanic zone, a rifted arc where the Pacific plate dives under the Australian plate and the crust stretches at the same time. That combination is a trap for melt. Basaltic inputs from the Mantle wedge feed into the lower crust, where magma spreads into sills, heats the rock, and melts it. The result is a thick, crystal-rich mush zone, silicic, volatile charged, and mechanically weak. It's a waiting room. The system can sit there quiet until a trigger tips it. What kind of trigger? Fresh injections of hotter magma that add gas and heat, fault slip that reduces pressure just enough for bubbles to link, or slow accumulation of volatiles as crystals grow, pushing a saturated pocket over the edge. The clues we have are the tremors and tilts that add up to a story. Lakebed surveys show uplift in parts of Taupo's floor, centimeters to decimeters over years, suggesting inflation of shallow sills. Seismic swarms tick along faults under the lake and nearby volcanoes. Gas chemistry flickers, CO2 rising ahead of water-rich steam in places. Each signal is subtle. Together, they trace pressure moving through a fragile architecture. History leaves floating signatures too. Pumice rafts, light, gas-rich rock fragments, have sailed from Taupo eruptions down rivers to the coast, then out to sea, drifting like warning notes. In the wider central North Island, the ash record shows bursts of activity that cluster, then lull. The pattern matches a crustal system primed by ongoing supply. Not constant eruption, but cycles of recharging, sealing, and breaking. Here's where the network tie matters. Subduction feeds arc melts, but deeper heat can modulate the background. The Haikurangi subduction margin is complicated. Slab geometry bends, fluids rise along a patchy interface, and the overriding crust is being pulled apart. If the regional mantle is warmer or more melt-rich due to broader anomalies, it lowers the threshold for the crustal mush to mobilize. In that frame, Taupo isn't an isolated bomb. It's a node in an active corridor that also includes calderas like Okataina and volcanoes farther northeast toward Wakakari White Island. The stakes stretch beyond New Zealand. A VI 6 to 7 from Taupo or its neighbors would reroute flights between the Americas, Australia, and Asia, throttling cargo and passengers for weeks or months. Air routes that cross the South Pacific hinge on stable ash forecasts. Southern Hemisphere agriculture would take a hit from both ash and sulfur-driven cooling, with New Zealand's own dairy and horticulture sectors absorbing direct impacts. Australia's eastern states could see haze, altered sunlight, and downstream logistics friction. Fisheries feel it too when ash changes coastal chemistry and clogs intakes. For people living around Lake Taupo, the threat isn't abstract. Hydrothermal fields dot the region. Steam vents and geysers mark pathways where fluids can shift quickly. Monitoring teams watch submillimeter tilts with INSAR and GPS, and they listen for swarms that hop from fault to fault under the lake. The honest challenge is signal to noise. Taupo is noisy even when it's fine. A rise in quake counts might be tectonic rattle, an uplift patch might be seasonal groundwater. Credibility rides on not overcalling the background. Micro story. A tour boat eases across Taupo's blue surface.
The captain points to a line of bubbles feathering the lake. Visitors take photos. On shore, a geophysicist checks a live feed. Tilt up a hair on the southeastern floor. A modest rise in CO2 at a shoreline vent, and a neat string of tiny quakes curving under Matutego Island. She logs it as a transient. 2 weeks later, the pattern fades. The note stays in the archive. Plumbing shift, no escalation. Zoom out along the Ring of Fire and you find other quiet monsters with similar architectures. Japan's Ira caldera beneath Sakurajima, frequent small blasts, steady inflation cycles. Indonesia's Sunda Arc, a mosaic of sills and mush beneath densely populated islands. Chile's southern volcanic zone, calderas like Laguna del Mal showing broad uplift tied to stacked intrusions. These systems share the crustal trap, melt-rich mush that's mostly solid but primed, waiting for a nudge. The playbook for Taupo and its cousins isn't panic, it's granular observation. Helium ratios to track deep inputs, gas flux networks to see volatile shifts, dense seismic arrays to map fault valve behavior, and lakebed sonar to watch inflation in real time. Models that tie these together turn noise into context, which swarms open pathways, which uplift patterns mean connected sills, which gas moves scream fresh basalt. Signals of pressure don't just rise vertically, they travel sideways along seams we're only now resolving. And when those seams light up across a region, the conversation changes from one volcano to a cluster poised on the same stress line. Signals that matter, helium, tilt, and shadows. If networks are real, the proof lives in signals that move before rock does. Start with helium. Deep mantle carries more helium-3 than the crust, which stacks helium-4 from radioactive decay. When we sniff volcanic gases and find elevated 3 He4He, it suggests fresh, deep-sourced melt joined the system. It doesn't mean eruption tomorrow. It means the fuel line is open. Watch how ratios change through time. A background plateau, a slow climb, then a sharper wiggle when new basalt intrudes and volatiles push upward. Helium is the whisper before the shout. Now watch the ground breathe. INSAR, satellite radar that compares phase changes between passes, sees millimeters of uplift or subsidence across wide areas. GPS, bolted into bedrock, tracks points in 3 dimensions, live. A millimeter tilt over 10 square kilometers sounds trivial until you do the math. That tiny dome represents millions of tons of rock shifting as sills inflate or deflate. The trick is pattern recognition. A round, smooth bowl hints at a shallow, pressurized sill. An elongated, lopsided swell might trace inflation along a fault-controlled reservoir. A seesaw, one side up, the other down, can mark a dike injecting laterally. Seismic waves give us shadows. P waves and S waves speed up or slow down depending on temperature, rock fabric, and melt. Persistent low-velocity zones point to hot, possibly partially molten volumes. But anisotropy, the way waves travel faster in certain directions, adds a layer. Crystals line up under stress, melt pockets align along fractures, and seismic energy responds. When anisotropy rotates over months beneath a caldera rim, it's a sign that the internal stress field is changing. Not random noise, reorientation you can tie to pressure migrating from one sill to another. Gas chemistry rounds out the picture. SO2 spikes tell you magma's involved. Hydrothermal systems scrub sulfur. CO2 comes up more easily and earlier, slips through water, and can climb before SO2 moves. So a sequence matters. CO2 baseline rises, INSAR shows a subtle dome, tiny quakes rattle a ring fault, then SO2 appears. That's the cadence of fresh input reaching shallower levels. But hydrothermal noise complicates everything. Rainfall dilutes vents. Seasonal heating changes background flux. You need dense networks, long baselines, and a habit of ignoring single-day spikes. The stakes are credibility and timing. Cry wolf on a noisy week and funding erodes. Miss a slow, coherent pattern, and you lose days when they matter most for aviation, evacuations, and power grids. That's why teams now fuse streams. A dashboard overlays helium ratios, tilt, seismic anisotropy shifts, degassing, and thermal anomalies from satellites. Algorithms flag cross-parameter alignments. A threshold isn't exceeded in one dataset, it's approached in 3. Here's a micro story from a control room that smells like coffee and dust. An analyst notices that a cluster of GPS stations on a caldera's southwest arc moved outward by 2 millimeters over 10 days, while a central station lifted 4 millimeters. Nothing huge. She clicks the anisotropy layer. Fast directions rotated 10 degrees along the same arc. She opens gas feeds. CO2 rose modestly at 2 distal vents, SO2 flat. She pings a colleague. Possible sill inflation, shallow, no sulfur yet. 2 days later, a swarm outlines a crescent under the uplift. The note goes out to civil aviation. Increased vigilance. Ash models updated, no closure. A week later, the dome relaxes. The system vented through cracks, not sky. Seismic.
Shadows also carry time. Temporary arrays, the kind field teams deploy on foot, tighten resolution. They pick up low-frequency earthquakes that hint at fluid movement, and tremor that suggests magma or hot water slipping through narrow spaces. When a low-frequency band drifts upward in pitch over hours, it can mean a conduit's narrowing under pressure. That's the minute-scale alert path for small blasts or hydrothermal eruptions. For supervolcano-scale systems, it's more about months, deepening tremor zones, swarms that step upward, and anisotropy rotating toward failure planes. Tilt meters, old school, insanely sensitive, live near active vents and fault scarps. They catch the fast stuff that satellites miss between passes. A sudden, clean tilt jump can mark a dike snapping open. Combine that with a rapid drop-in well pressure at a geothermal borehole and a string of long-period quakes, and you've caught a valve opening. The next question is whether it sticks or seals. Data gaps are real. Cloud cover spoils INSAR. Snow buries vents. Politics delay sensor repairs. That's why redundancy matters. Multiple satellites, cross-border gas networks, community scientists maintaining backyard CO2 monitors that feed open databases. The more eyes, the better the odds that a false alignment gets called out and a real pattern gets caught early. And now the hard part, translating signals into decisions. A millimeter today doesn't ground a fleet, but a slope and uplift over weeks, gas chemistry stepping through the expected sequence, anisotropy turning, and swarms migrating. Together, they justify pre-positioning masks, checking food stocks, rerouting flights before the ash, layer those signals across continents, and patterns start to line up between nodes. That's when a local story begins to look like a regional arc, bending towards synchronized stress. Synchronization. How separate systems fail together. Layer the signals across borders, and a different thread appears. Not one mountain blowing, but several systems leaning at once. Volcanoes don't coordinate, but the planet does. Climate, plates, and ice push and pull together, and calderas respond on their own thresholds. The danger is timing. Separate engines nudged in the same decade, each crossing its line for its own reason, yet adding up to a global shock. Start with climate coupling. El Niño warms the equatorial Pacific, shifts rain belts, and rewires wind patterns from the Andes to Indonesia. Those winds steer ash and sulfur. They also change how aerosols live in the stratosphere. After a big eruption, El Niño conditions can keep sulfate plumes lingering and drifting into sunlight-sensitive regions, cutting more radiation where crops already strain. Flip to La Niña and monsoon belts intensify, dumping rain on ash-covered fields that turn to cement. The atmosphere sets the stage. The volcano decides the act. There's a feedback loop, too. Aerosols cool the surface, especially over land, changing pressure gradients that steer storm tracks. Cooler continents weaken monsoons, reduce wet deposition of sulfate, and paradoxically help aerosols persist longer. That extends the forcing from a VI 6 to 7 into a second growing season. If 2 such eruptions land within a couple of years, say one in the tropics, one in the mid-latitudes, the combined aerosol tails overlap. Not additive like numbers, but compounding, because sunlight is the bottleneck for photosynthesis and temperature thresholds are unforgiving for grains. Meanwhile, plates have their own rhythm. Subducting slabs don't roll back smoothly, they lurch. When a slab's hinge retreats, the overriding plate stretches, lowering pressure in the mantle wedge and increasing melt supply to arcs. That's not a daily switch, it's a multi-decadal phase that lights up a chain. Look at historical clusters where multiple arc volcanoes stepped up activity together, then quieted as rollback slowed. Layer that on top of a warm El Niño decade, and the odds of 2 significant eruptions landing close in time rise. Delamination adds another pulse. When the dense root of thickened crust peels off, hot mantle surges upward. Regions like Anatolia and parts of the central Andes show geochemical signs of that replacement.
It's a one-off in a given place, but across continents, several provinces can reach that peeling moment within the same century. Each pushes more basalt into the lower crust, priming mush zones above. None of them cares about our calendars. Their clocks are mineral and stress. Then there's loading and unloading, ice and oceans as silencers and triggers. When ice sheets retreat, the crust rebounds and the weight on shallow magma systems drops. That pressure release can free bubbles, lower the threshold for dike propagation, and raise eruption probability. After the last deglaciation, high-latitude volcanoes in Iceland and parts of North America saw elevated activity. Today, mountain glaciers are in retreat, and ice caps like Vatnajökull are.
The rates aren't Toba-scale triggers, but for intermediate systems, VI 6 to 7 candidates, they matter. Sea level rise loads ocean basins and unloads continents, adjusting stress along coastal arcs in subtle ways that can bend fault valve behavior. Historical clusters hint at synchronization. In the early 1600s, several tropical and high-latitude eruptions bracketed a colder, famine-prone period in parts of Europe and Asia. The 1808 unknown eruption and Tambora in 1815 stacked, forcing into the year without a summer. None was a VI8. Together, they torqued climate and harvest beyond what anyone would have done. That's the model to watch now. A decade with 2 or 3 VI6-7s, well-placed in latitude and timing under climate phases that stretch aerosol lifetimes. And here's the urgency. We're already seeing overlapping aerosol events and rerouted corridors in the same years. The window for coincidence is opening. What nobody knew until the networks got dense was how stress signals might ripple across regions. A rollback phase in one subduction zone can coincide with increased deep seismicity beneath another as global mantle flow reorganizes. The link isn't a pressure wave racing through rock. It's shared boundary conditions changing together. Plates shift speeds by 1%. Mid-ocean ridges adjust melt supply. Hotspots interacting with ridges redistribute warmth along corridors. Calderas sitting on the edges of these fields feel the incremental nudge, enough to take a pre-stressed sill across its failure line when a local injection arrives. The stakes are markets as much as maps. A single VAI7 in the tropics can trim global grain yields for a season. Add a Northern Hemisphere VI6 2 years later, and you get a second dip while inventories are already drained. Futures markets spike, fertilizer prices chase logistics, and countries impose export bans. Aviation takes repeated hits as ash advisories shutter corridors across the Atlantic, then the Pacific. Insurance re-rates risk. Credit tightens for shippers who suddenly can't guarantee delivery windows. None of this needs a super eruption. It needs coincidence multiplied by coupling. Microstory. In Chicago, a grain trader watches satellite-derived aerosol optical depth tick up over the Indian Ocean. 2 weeks later, a mid-latitude eruption ash cloud clips transatlantic routes. Freight shifts to slower sea lanes. A heat wave breaks early under a dimmer sun, and harvest models shave 5% off expected yields. He calls a client. We'll need to roll contracts. In Naples, an energy manager orders spare filters for gas turbines months ahead of schedule. In Auckland, a logistics planner books extra cold storage because flight delays mean fruit sits longer. None of them talk to volcanologists. They react to the synchronization they can't see. So how do separate systems fail together? Through shared climate phases that stretch aerosol impact, tectonic rhythms that pulse melt supply across arcs, and loading cycles that bias thresholds in the same era. Add a global economy tuned to efficiency, and the amplifiers are already in place. The urgency is simple. The same dials that aligned before are leaning the same way again. El Niño phases, retreating ice, ridge hotspot coupling, while multiple calderas show subtle simultaneous pressure tells. Everything was about to change when these cycles aligned last time. We're entering another alignment window now. And there's one region built like a loaded spring, where crustal stress, torn slabs, and dense cities sit on the same line. The Mediterranean Supervolcanic Arc. While that synchronization builds, the Mediterranean sits like a faulted pressure cooker. Densely populated shores wrapped around torn slabs and hungry calderas. Naples is the postcard, but the engine runs beneath the entire Campanian plain. Campi Flegrei and Vesuvius don't just share a skyline. They share stress, fluids, and a history of roofs failing when the crust tires. Start at Campi Flegrei, the burning fields. It isn't a mountain. It's a 12 to 14 kilometer caldera packed with neighborhoods, ports, and a stadium.
The ground there rises and falls in slow breaths called bradyseism. In the 1970s and 1980s, Pozzuoli heaved upward by more than a meter in pulses. Streets cracked. The harbor became too shallow for boats. Tens of thousands were evacuated, not because lava was at the door, but because the lid was creaking. Since then, uplift cycles have come back, slower, quieter, but persistent. Gas vents along Solfatara and Piscarelli pulse hotter. CO2 and steam whisper about deeper inputs. Across the bay, Vesuvius keeps its own counsel. The 79 CE eruption that buried Pompeii set the template, but the volcano's later phases tell a subtler story. Long repose, then a switch into centuries of frequent activity, then quiet again. It's a valve on the same regional plumbing, where the African plate dives under the Apennine belt and the crust above stretches. Extension thins the lid. Subduction feeds fluids into the mantle wedge. The result is a crust riddled with sills, faults, and mush, primed for pressure to migrate sideways as much as up. Bradyseism isn't just a curiosity, it's a meter for a stressed lid. When Pozzuoli rises, it means shallow sills are pressurizing, either by magma edging in, by hydrothermal fluids expanding, or both. The debate turns on ratios. How much of the uplift is elastic inflation from melt versus pressurization of a hot, water-rich sponge? Gas chemistry leans both ways. SO2 is often scrubbed, CO2 sneaks through. Helium ratios tilt toward a mantle contribution, but they're mixed. Deep signal stirred into a crustal brew. The honest read is that the system alternates between fluid and melt dominance, with each cycle weakening the roof. Zoom out to the regional stress. The Apennines are stretching, their backbone unzipping along normal faults that tilt blocks and open space in the upper crust. Meanwhile, tomography shows the subducting African slab is torn and retreating in patches under the Tyrrhenian. That tear acts like a slab window. Hotter asthenosphere flows up behind it, raising the thermal baseline. Crust caught between extension above and warm flow below becomes a sieve. Melt collects in sills beneath coastal plains, and fluids ride fractures toward caldera rims. When seismic swarms rake the Campi Flegrei margin and microquakes tick under Vesuvius on the same week, that's the stress field talking. The neighborhood dynamics matter because small choices cascade in tight spaces. A VA5 from Vesuvius, or a phreatomagmatic sequence from Campi Flegrei would mean ash over Naples, grounded flights across southern Europe, and a grid dealing with simultaneous cooling demand spikes and maintenance delays. Ports at Naples and Pozzuoli are lifelines for fuel and food. Ash turns docks into slip hazards and clogs diesel filters on cranes. The archaeology that draws millions becomes a vulnerability. Stone and mortar don't love acidic ash and weeks of damp, dim air. Microstory. A baker in Pozzuoli opens at dawn to find hairline cracks reappeared across the shop's tiled floor. He's seen this before. That week, the bradyseism gauge ticked upward another centimeter. In a lab across town, a geochemist logs CO2 increases at Piscarelli, then curses when a rainstorm knocks out a sensor. In Rome, civil protection runs a tabletop drill. Ashfall maps overlaid on hospital routes, ferry schedules, and school closures. No one wants to call an evacuation that doesn't need to happen. No one wants to miss the one that does. The broader Mediterranean Arc stacks more loaded springs. The Phlegreian fields tie west into the Tyrrhenian seafloor, where back arc basins have opened and shut, leaving a quilt of thin crust and magma storage. The Aeolian Islands ride a separate pulse. Shallow plumbing under Stromboli puffs daily, while deeper inputs feed Volcano and Lipari in fits. To the southeast, Etna, fed by a complex mix of slab fluids and deeper anomalies, shoves dikes toward the coast, sometimes dumping ash on Catania's runway 3 days in a row. None of these is a super eruption factory today, but together they form a corridor where melt supply is enhanced by slab geometry and crustal thinning. What ties this to the global network is the deep link. Seismic images suggest slower mantle beneath the central Mediterranean than you'd expect if the slab were intact. If that's real, it means extra warmth and a longer-lived melt budget under crust that's already fractured. That's how a region
stays restless for centuries. It never quite freezes. The sills keep inflating and deflating, bradyseism keeps resetting the sidewalks, and gas keeps finding new vents down alleys and inside courtyards. The stakes scale quickly. Europe's population density, aviation hubs from Rome to Munich, and interconnected power grids mean a VI 5 to 6 in this arc is not a local emergency. Ash closes corridors from Spain to the Balkans in hours. Sulfur aerosols shave light off vineyards as far as France for a season. Gas turbines in Italy and Germany swap filters on a schedule that assumes blue skies, not silicate dust.
Fiber optic cables don't care about ash, but the people who maintain them do. If roads glaze and ports stall, repairs wait. And there's the cultural weight. Evacuation in Naples isn't just lanes and buses. It's asking people to leave homes and neighborhoods that survived wars and earthquakes, under leaders whose credibility depends on not gambling with livelihoods. The stakes are intimate. Grandparents who won't leave, businesses that can't survive a false alarm, and streets where a bad call lingers for decades. That's why the signal thresholds matter. Helium bumps that hold for weeks, uplift that accelerates, anisotropy rotating into failure planes. False alarms corrode trust. Missed calls cost lives. In a synchronized decade, you might face those choices twice. This decision would haunt them because across the Atlantic, another corridor hides under ice, feeding its own expanded melt budget. While Campi Flegrei negotiates with its lid, the North Atlantic is busy loading and unloading its valves. Meanwhile, across the Atlantic, a silent giant grows under ice. The Iceland, Jan Mayen Corridor. Meanwhile, across the Atlantic, a silent giant grows under ice. Iceland sits where a mid-ocean ridge meets a hotspot, two melt machines overlapping. The ridge pulls plates apart, lowering pressure so the mantle melts. The hotspot adds extra heat from below. Together they flood the upper mantle with magma, more than a ridge alone would make, and that surplus spreads along a corridor north toward Jan Mayen and south down the Reykjanes Ridge. It's not just a dot on a map, it's a belt, and it stays busy. Iceland's lesson for modern systems came in 1783-84 at Loki. No big ash mushroom, no city buried in seconds, just months of fire fountains along a fissure, pouring out basalt and belching sulfur. The haze drifted over Europe. Crops yellowed. Livestock died after eating grass coated with fluorine-laced ash. Grain prices rose. Famine sharpened. It wasn't a VI-8, not even close. But the sulfur famine was enough to knock climate and food for a year, and the social stress that followed became part of the era's unrest. That's the corridor's power. It can hit the atmosphere hard without a single towering blast. Today, the magma supply looks organized by the Plume Ridge interaction. Seismic images show a broad, low-velocity mantle under Iceland, fanning into the ridge like a tree root. Melt focuses beneath central volcanoes, Grímsvatn, Bárðarbunga, Katla, and also along fissure swarms that step outward. Northward, the Jan Mayen microcontinent marks a kink where ridge geometry and deeper warmth converge. Eruptions there are rarer, but the corridor's thermal field reaches past Iceland's shoreline. Ice adds a trigger. Vatnajökull, Europe's largest ice cap, loads the crust. Over decades, that weight thins as the climate warms. Unloading changes pressure in the upper crust and shallow mantle. Lower pressure makes it easier for bubbles to form in magma, easier for dikes to lift into fractures, and faster for decompression melting to add fresh basalt to the budget. After the last deglaciation, Iceland's eruption rate spiked. We're not repeating that exactly, but the physics rhyme. Losing ice tips probabilities upward for the next century. In 2014, a dike from Bárðarbunga snaked 48 kilometers beneath the ice to Helium and erupted for months, releasing SO2 on a scale not seen in modern Europe. We've seen how this plays out in slow motion. Planes kept flying by dodging the plume, but towns downwind coughed through blue haze days. The ash load stayed modest, the gas load did the damage. Flights into and out of Scandinavia and the UK rehearsed contingency routes. Power plants checked intake filters daily. That was a rehearsal. A Loki-scale repeat would stretch that rehearsal into a season. Under the ice, central volcanoes reload on their own clocks. Grímsvatn pops often. Its gekolopes, glacial outburst floods, burst from subglacial lakes when ice dams fail. Katla sleeps less soundly than its fame suggests, with frequent subglacial tremor that keeps vigilance high. Bárðarbunga flexes with inflation and quiet subsidence after Helium. Reykjanes, quiet for centuries, woke in 2021 with shield-style basalt after swarms and steady uplift, then kept pulsing in subsequent years with fissures that opened within walking distance of roads. Each episode confirms the corridor is awake along multiple seams. Deep ties matter for northward spread. Jan Mayen's Berenberg sits on a microplate boundary where hotspot influence may enhance melt supply. The stakes there aren't cities, they're air routes and North Atlantic weather corridors. Ash and sulfur in that latitude bend storm tracks subtly and force airlines to juggle polar routes during windows of clean air. Fisheries face their own exposure.
Ash falling into key spawning zones changes chemistry and light, while SO2 alters near-surface pH in pulses that stress larvae. None of this requires a catastrophic blast, just sustained degassing along the corridor. Infrastructure feels the grind. Europe's aviation network threads through North Atlantic airways that hinge on predictable winds and open corridors. An Iceland Jan Mayen gas-rich episode forces altitude and route changes that burn more fuel and jam schedules. Subsea cables mostly ignore ash, but maintenance ships don't. Ports in Reykjavik and Akureyri slow when visibility and corrosive haze wrap cranes and decks. Hydropower is robust, yet high-voltage lines need cleaning cycles tightened if conductive films build on insulators. Spare parts lean on flights, flights lean on air quality. Here's a human-scale moment. A meteorologist in Keflavik pulls up a forecast showing a low-tracking ash south toward the UK. On the same day, a SO2 plume drifts east. He flags a complex advisory. Ash concentrations below engine tolerance at cruising altitude, SO2 at levels that trigger cockpit sensors. Airlines scramble to separate risks, fly under the sulfur, around the ash. Dispatchers redraw lines hour by hour. It's not panic, it's attrition. The deep physics keep the corridor topped up. The plume at Iceland keeps sending heat into a mantle stirred by ridge flow. Melt doesn't rise straight up. It funnels along gravity and stress gradients, pooling where the lithosphere is thinnest and fractures are primed. As ice continues to lighten the lid, more dikes will test those seams. Most will stall. Some will break surface quietly. A few will run long, and the sulfur will matter more than the ash again. And this corridor connects back to the global network. If aerosol loads from a North Atlantic fissure season overlap with a mid-latitude eruption elsewhere, the combined dimming stretches food stress into a second harvest. North Atlantic flights reroute in the same quarter that Mediterranean corridors choke on ash. Fisheries, grids, and cold chains feel it in parallel. Signals converge on timing, not destiny, but windows when odds stack. Which brings us to a thorny idea. Are we overdue or just bad at clocks? The myth and math of overdue. If the Iceland Jan Mayen corridor teaches anything, it's timing without a timer. People want a date. Volcanoes offer probabilities. The word overdue sneaks in because we love averages. Add 3 big eruptions, divide by gaps, and draw a line through history. But the math behind eruptions isn't a metronome. It's closer to dice with loaded sides that change weight over time. Start with the simplest model, a Poisson process. In that world, eruptions happen with some average rate, and each year is independent. If the average is 1 VEI7 every few hundred years, then waiting longer doesn't make the next one due. The odds reset each year. That's clean, and often wrong. Geological systems age, they seal and unseal. Melt supplies pulse, stress accumulates, independence breaks. Clustered reality shows up in the record. Quiet centuries, then flurries. So we step to renewal models. Think of a reservoir recharging to a threshold. If melt influx, volatile saturation, and roof strength set that threshold, then time since last event matters because the system evolves. But matters isn't schedule. Reload rates vary with deep heat and shallow plumbing changes. 1 century of robust basalt input can rebuild pressure fast. A dry spell can freeze the mush and extend quiet for millennia. Even within one volcano, thresholds shift as caldera faults anneal, hydrothermal systems carve pressure release valves, and crystals grow to change viscosity. For VI8s, uncertainty balloons, the global count over a couple million years is small, and deposits are hard to measure precisely. Some calderas left more ash than we can confidently total, others lost evidence to erosion or subduction. When researchers fit recurrence intervals, the error bars are brutal, tens to hundreds of thousands of years wide. That's why overdue for a VI8 anywhere on Earth is sloppy talk. The right question is whether the preconditions that make VI8s possible, large melt volumes, high volatile budgets, weak roofs over wide areas, are present and trending upward in specific systems. That's physics, not folklore. What's overdue isn't a date, it's pressure. In practice, scientists track what can actually cross a line. Melt fraction approaching connectivity in silicic mush, volatile saturation nearing.
Runaway exsolution and pore pressure rising in key sills beneath ring faults. Those variables don't care about an anniversary.
They respond to basalt injections, decompression from ice loss, and stress transfer during earthquakes. When we say a system is maturing, we mean those metrics are drifting toward thresholds more often than away. Risk framing helps untangle emotion from math. Hazard is the physical possibility, eruption size and style. Exposure is what's in harm's way, people, planes, crops. Vulnerability is how breakable those things are. Filters, storage, seed diversity, redundancy. We've increased exposure massively. More planes aloft, more megacities near coasts and arcs, longer supply chains. We've lowered vulnerability in some places with better monitoring and playbooks, but we've also shaved buffers thin. The same VI6 that was a regional crisis a century ago is a global logistics problem now. Multiplied by synchronized odds, and a decade can wobble without a single super eruption. Uncertainty isn't ignorance. We know enough to bound probabilities. VI6 events likely occur multiple times per century. VI7s, a handful per millennium on average, but clustered. VI8s, rare on human timescales, remain low probability, high impact tail risks. Tail risk isn't a ghost story. It's the part of the curve that hurts if you plan for medians. For aviation, that means ash tolerance standards, diversion fuel planning, and sensor integration. For food systems, that means larger grain reserves, fertilizer stockpiles, and cold chain resilience when routes bend. Credibility hinges on plain language about uncertainty. We don't know isn't a shrug, it's a scope. When a monitoring team says uplift is rising but sulfur is flat, they're not hedging. They're telling you magma's influence is possible, but hydrothermal pressurization is likely. When a global dashboard flags CO2 rises across an arc while anisotropy rotates beneath two calderas, it's not doom. It's a nudge to recheck routes, top up inventories, and run drills without sirens. There's a psychological trap here. Humans anchor to round numbers. 600,000 years since Yellowstone's last giant, therefore due. But the Snake River Plains hotspot track and the current crustal architecture don't map to a repeat on that cadence. The Mediterranean's last caldera-forming events don't set a clock for Pozzuoli sidewalks. Taupo's het doesn't predict the next decade. Its current lake floor tilt does. We're better served replacing the word overdue with conditions trending. Conditions trending to what, at what rate, and with which leading indicators. What would make overdue meaningful in practice? Converging signals that cross pre-agreed thresholds, sustained uplift acceleration over months, helium ratios stepping above long-term baselines across multiple vents, seismic anisotropy rotating into expected failure orientations, and gas chemistry shifting from CO2 dominant to SO2 present. Those aren't blog lines. They're trigger points for moving aircraft, staging masks, and topping reserves. Set them in peacetime. Update them with each quiet year. Publish them so trust survives the noise. We built a world that treats averages like promises. Volcanoes deal in ranges and states.
The myth of overdue tempts false certainty. The math says live with probabilities, watch the right dials, and accept that preparation beats prediction, especially when the next meaningful shift won't arrive on a date circled in red. What scientists can't stop, but can soften. Here's the hard truth. You can't drain a continent. There isn't a valve you open to let a caldera relax. Drilling to bleed, a supervolcano sounds tidy until you run the numbers. Wellbores are straws in an ocean, and puncturing a pressurized mush can make valves not relief. Even controlled cooling is fantasy at the scales that matter. The energy in a large silicic reservoir dwarfs anything we can move with pumps or pipes. So scientists don't sell prevention. They work the margins where margins matter. Those margins start in the air. Aviation is where minutes count and data wins. Volcanic ash advisory centers already fuse satellite retrievals with dispersion models. The next step is richer sensor networks on planes. Forward-looking infrared for ash, SO2 sniffers tied to cockpit alerts, and engine health monitoring that flags early glassing. With those in place, airlines can fly narrower corridors with confidence instead of shutting whole regions. It's not stopping ash, it's turning a blind map into a scalpel. Food is the slower clock, but it cracks without warning. Sulfur haze trims sunlight, chills a growing season, and shifts rain. You can't change the sky, but you can change buffers. Grain reserves sized for a bad year need to cover a double hit, 12 to 18 months. Fertilizer stockpiles matter because sulfur-driven cooling plus ash-washed soils push yields down unless nitrogen is ready at the right window. Seed banks aren't museum pieces. They need distribution plans so shorter season varieties reach farms fast when a dimmer sun cuts ripening time. Power rides on filters. Ash is glass, it chews turbines, clogs intakes, and shorts insulators when it cakes wet. Utilities can pre-buy and pre-place high-efficiency particulate filters, silicone grease for insulators, and spare blades for gas turbines. Hydropower is robust, but ash in reservoirs changes turbidity and friction losses. Planning for extra drawdowns and dredging cycles keeps turbines from grinding. Grid operators can run ash mode playbooks, lower loads on vulnerable lines, rotate maintenance to align with plume windows, and coordinate with aviation so parts and crews don't strand. Monitoring is the nervous system, and it scales. Global INSAR constellations, multiple radar satellites with short revisit times, turn millimeter tilts into live theater. Open telemetry for gas sensors and seismometers, shared across borders, means a small institute's vent data feeds a continent's dashboard. Helium labs that run on shoestring budgets become critical nodes. A modest fund that keeps their mass spectrometers warm through quiet years pays off when ratios step. The tactic is simple. Redundancy. Clouds block one satellite, another flies. A seismometer goes down. A citizen sensor fills the gap. Policy is the glue. Aviation reroutes are only as good as the rules that allow dynamic thresholds, engine ash tolerance standards, SO2 cockpit thresholds, and a common language for hazard bands. Food policy needs trigger points. When aerosol optical depth passes a line for a region, export bans phase in. Transparently, and emergency grain swaps unlock. Fertilizer flows shouldn't bottleneck at customs during the worst month of a planting calendar. These aren't hero moves. They're memos written in peacetime that keep politics from improvising under a gray sky. Local moves matter most where risk sits on sidewalks. In Naples, drills that move buses along pre-planned corridors aren't theater. They're rehearsals that reduce panic. Mask stockpiles sized for ash, not viruses, keep lungs clean when grit floats for weeks. Schools that can go dark without losing meals prevent families from crowding roads during advisories. Around Taupo, boat captains linked to lake floor tilt alerts can clear zones before a hydrothermal burst. In Iceland, towns practice closing air intakes and switching ventilation paths on SO2 days. Small steps that keep clinics open and elders breathing. Here's the 3 a.m. call that makes this real. A volcanologist's phone buzzes on a nightstand. An automated alert says a regional dashboard flagged uplift acceleration and a CO2 rise at 2 vents. She pads into a kitchen, opens her laptop, and watches tremor thicken under a caldera rim. She doesn't call evacuation. She calls civil aviation to tighten routes for 48 hours and pings the agriculture ministry to push a fertilizer release to farms 1 week early, just in case. She messages a power utility to inspect insulators before a forecasted wet ash fall. 12 hours later, SO2 appears and a small eruption throws ash into flight levels. Routes were already bent. Filters were already on the truck. That's softening. Engineering limits exist, but small technologies stack. Low-cost air sensors in neighborhoods turn ash advisories into street-level maps. Portable de-ash rigs for solar farms keep panels producing under a gray veil. Greenhouses with supplemental lighting bridge are critical. Month for seedlings when sunlight dips. Cold chain nodes add 20% surge capacity to absorb flight delays without dumping food. Insurance products reward ports that harden against ash slip and corrosive haze with covered retrofits. All of this depends on trust built during quiet. Open data lowers rumor heat. Clear thresholds make early calls defensible. Cross-border exercises reveal where it's not our jurisdiction lives in the paperwork and breaks it before it breaks you. You can't stop a reservoir from failing when its physics say go. But you can stop the cascade from turning an eruption into a systemic shock. So if the ground truth is messy, the honest question isn't whether we can prevent the blast, it's how early we can move the pieces that bend the aftermath. The plain language risk picture. Let's strip the jargon and talk odds you can actually use. This century, we're likely to see multiple VEI 6 eruptions and a decent chance at a VEI 7. That's not sensational, it's how the long record behaves when you zoom into 100-year windows. A single VEE 6 can darken skies over a continent for weeks, trim crop yields, and ground flights for days to weeks. 2 in a decade, well placed in latitude and season, stress food and freight together. VEI 7s are rarer but on the table. Think more sulfur, wider ashfall, and multi-season climate impacts. Not the end, but a hard couple of years where sunlight dips just enough to hurt grains, with price spikes and export bans cascading across borders. VII-8, the supervolcano tier, lives in the low probability, high impact tail. It's possible in a human lifetime, but the honest math says plan for 6s and 7s, insure against an 8. Now layer real life. The hazard isn't just ash and sulfur, it's how those collide with the systems we built. Picture a chain. A VI-6 in the tropics injects sulfate, dims a growing season, and nudges yields down 5 to 10% in sensitive regions. 6 months later, a mid-latitude VI-6 snarls North Atlantic flights for 2 weeks during harvest export. At the same time, an animal-borne virus spreads through stressed livestock networks because cold chain delays keep animals and vaccines in the wrong places. Energy prices pop as gas turbines need maintenance on the same week's ash advisories close corridors. No single link breaks the world. The sequence tilts it. So what should you watch without living online? A few signals matter. Satellite aerosol optical depth tells you when sulfate haze is building after an eruption. If AOD stays high into the second growing season, expect persistent yield pressure. Aviation advisories from volcanic ash centers signal acute disruption windows, days to weeks, where routes bend and cargo slows. National agriculture bulletins that mention insulation reduction or shortened growing degree days are plain language clues that sunlight and temperature shifts are landing. If those three align, haze high, flights rerouted, and crop notes flagging dimmer sun, you're in a compounding period. At home scale, resilience is boring on purpose. Breathable air comes down to fit and filtration. N95s are better for errand days under ash, plus a small stock of replacements. For houses, a simple box fan with a HEPA filter turns a room into a clean air zone during dusty spells. Water matters because ash fouls gutters and clogs small filters. Keep a gravity filter rated for particulates and a few spare elements. Food redundancy isn't apocalyptic. Aim for 4 to 8 weeks of staples you actually eat, rotate it normally, with extras that don't need long cook times if power is intermittent. If you run a business, think in buffers. Can you tolerate a 2-week shipping delay without missing payroll? Can you swap suppliers across regions if a flight corridor closes? Do you have spares that ash will chew? Filters, belts, lubricants on your shelves instead of on back order? These questions matter more in a year when 2 eruptions land than in any calm year. And that's the point. You don't get a calendar invite. You get a haze forecast and a freight email. Communities scale the same logic. Local clinics that add portable air cleaners and stash extra inhalers turn a sulfur week into an inconvenience, not a crisis. Food banks that pivot to shelf-stable distributions for a month keep roads clearer when ash makes driving risky. School districts that can remote teach for a week without scrambling prevent substitute shortages during mask advisories. None of this needs a volcano to justify it. Fires and dust storms deliver the same tests. The volcano frame just forces you to think about the second and third month, not only the bad week. Where do you find reliable volcano signals without noise? National Geological Surveys and volcano observatories post status pages with simple color codes, green to red. Watch trends, not colors. If uplift is accelerating and gas reports show CO2 rising across multiple vents for weeks, that's pressure building. If SO2 appears after CO2 and tilt steepens, that's fresh magma climbing. Global dashboards like the VAC maps or NASA's aerosol pages give you the sky side. Set a couple of bookmarks. Check them when a headline breaks. Not every day. Now the uncomfortable part. Tail risk. A VI-8 would mean multi-year cooling and logistics failures that blow past stock more rice. That's why the system level moves in the last section matter. Grain reserves, aviation playbooks, power filter kits, seed distribution. For an individual, tail risk translates to skills and networks. Can you share air filters with a neighbor? Can you pool orders for spares? Can your community center act as a clean air hub? Tail risk planning thrives on cooperation because no one buys a scrubber for the neighborhood alone. Open loops to hold in your head. Helium ratios at key calderas, deep fuel signals, lake floor tilt at Taupo, shallow inflation, bradyseism at Campi Flegrei, lid stress, SO2 from Iceland and Jan Mayen, gas seasons. You don't need to memorize numbers. You need to notice when multiple dials move in the same month. That's when you top up supplies, advance maintenance, and check in with the people who need help under a gray sky. The network keeps moving because the planet does. Your edge is to move early, in small ways when the dials lean the same direction. That's not fear, that's timing. Meaning, living with a restless planet. We built our cities, markets, and myths during a quiet slice of geologic time. It felt normal because it lasted long enough to teach our grandparents what to expect from the sky. The planet never promised that rhythm. It breathes through heat and fracture, and we live between breaths. That isn't a threat, it's a setting. The meaning isn't to fear the next plume. It's to live as if cycles exist, and to be ready when they tighten. Humility helps. Volcanoes aren't villains. They made the soils that feed us, the metals that wire our lives, the land we stand on. Accepting their timescales doesn't make us fatalists. It makes us better planners. When we trade overdue for conditions trending, we step out of superstition and into stewardship. We stop waiting for a date and start watching the dials we can measure. Continuity is our edge. People adapt when knowledge moves faster than rumors. A pilot who trusts a live SO2 feed flies safely through a maze that would have grounded fleets a decade ago. A farmer who hears that sunlight will dip by 5% for a month plants a shorter season variety and still makes the mortgage. A school that practiced ash days keeps kids learning and parents off jammed roads. The lesson repeats. Small, practice moves beat big, improvised ones. Responsibility scales from kitchen tables to cabinets. Funding a helium lab isn't glamorous, but the ratio it measures buys days for aviation planners. Stocking masks for ash instead of speeches for press conferences isn't heroic, but it saves lungs. A regional grain reserve that rotates stock before it expires keeps politics cooler when exports pause. None of this stops magma. All of it stops panic from doing more damage than ash. All without paralysis is a skill. Stand at a caldera rim and let your stomach drop. Then open the dashboard on your phone and see the tilt line just stay flat. Walk a city street that rises a centimeter in a month and feel the ground alive. Then watch a civil protection drill empty a square quietly in 10 minutes. Fear shrinks when practice expands. Risk without fatalism means choosing a first move before the siren and a second move after the first goes well. It means neighbors who know who needs help on mask days and which clinic has spare filters. It means leaders who publish thresholds before the plume and stick to them when the comments burn. The decision that matters when ash starts to fall is the one you made last month. Which data you trust, which buffers you topped up, and which number you call first. The planet breathes through fire, and we live between breaths. Our job is to listen closely enough to move early, not perfectly. If you want honest signals before the noise, subscribe. Watch next, how a VI-6 grinds the food system in 30 days. Flight paths, sulfur, and a map we're screenshotting. Turn on alerts, the network won't wait.